There it goes. All right. Hey, everybody. Welcome, welcome, welcome again to Astronomy Daily Live. It's 2 hours UTC, and here we go again. Hey, hope everybody's doing well out there in the universe and the world. And yep, everything's going well here. Took the day off to just sort of not do very much, just some casual working around, still working on trying to work out all the photometry using my telescope and CCD camera. So I was working on that a little bit today too. Gotten to a point with that project where I think I've gotten rid of all the bugs in the software and all the um, algorithmically making the measurements and everything. I think everything is nice there. I'm seeing results that I am sort of expecting to see, but I'm not too happy with the results. So I think the results are correct, but yeah, they could be a lot better. And so I am looking at ways of making improvements there. So in the meantime, on the panel once again is Bobby. Hey there, Bobby. What's happening?
Hey, hey, what's up?
Hope all is well. Had a little bit of excitement, huh?
All was almost not well earlier tonight.
Well, that's not very fun. What happened to cause you this grief?
So I was on my way to go to the store, usually like either walk or bike, and then like some dog almost came on, ripped a hole in my pants, but he almost would have bit the shin off of it.
Wow. Yeah, that's no good. That's no good. It's sometimes it's hard to control dogs, right? But if you're a halfway decent owner, then you sort of learned that kind of responsibility. So hopefully, Mr. Doggy won't be doing that again, because that is definitely not very acceptable for sure. So hope everybody's okay there. I've got the regular hydrogen hydroxide again tonight. I've already actually drunk out of this, so I'm not quite full. I'm about a 3/4 here. So cheers.
Yeah, I'd like to welcome Uncle Bill, Doran, Yellow, and Tom Van Scotter in the chat.
Hey there, everybody. Nice to see you in the chat. I'm gonna grab that too. Busy day. Yeah. I've sort of noticed a little bit there. Uncle Bill. So yeah. Hope all is well there. Whatever you're working on, they're in good hands. They're in good hands for sure. So hey there, Tom. Nice to see you. Atta. Oh, cool. So you're going out back on the acting train for a little while. Cool. Well, safe travels, and make sure to have a good time. That is number one. And number two, have a
Lots of more Broadway musical.
Yeah, very cool. So yeah, hope you have a good time with that. Yeah, for sure.
I wonder how long she's been in acting.
I don't know. Maybe she'll let us know. Yeah, that's something that I have never, ever done. Well, Okay. All right. That's not exactly true. Was I I was in a play in grade school, right? I don't remember what grade it was, but I played Galileo, of course, and but I don't know if that necessarily counts as acting because yeah, I don't I I don't really consider that acting. so, so
Now, I think some of the best plays you would ever would go to is like an interactive play. I was in one of those in my sophomore year,
hmm.
and there was a part when there was going to be like a major fight, and you're supposed to like throw a box at someone. I actually throw it right in the kisser of somebody else.
Oh, N- not planned, huh?
Nope.
Oh, ouch, ouch. Now I like going to plays, right? Um, well, yeah, I haven't actually been to a lot of plays. I guess I've been to a lot of I guess you'd call them musicals, right? I've seen Cats. Um, I've seen I've seen a couple of operas. Don Giovanni. I'm trying to remember another one. So yeah, I've been to a couple of musicals, um, and
With a
maybe
suit and tie or something or what?
no, 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 no. You just come as you are, and so, but yeah, yeah,
Usually
really, really nice.
operas and plays like these, I usually like really get dressy and stuff.
That's cool. No, I am not the dressy type. I don't know if you can tell that or not, but I am definitely not. Uh, I'm just not the dressing up type. I have absolutely no dress up clothes whatsoever. Right? I've got
You mean
t-shirts.
Sunday wear?
Nothing like that whatsoever at all. It's like t-shirts and jeans and sweats and a couple of clean shirts. That's about it. So yeah, nothing dressy here. I think I've worn a suit twice in um, my entire life. So I think 2 times or 3 times. I forget exactly. So
Yeah, and also has got something about her acting, and also I thought that you was a real male fashion plate.
yeah, nope, not in the least. I am the opposite of that. Whatever that is, I'm the exact opposite of that. For sure.
Now I haven't seen Report a Week yet, but I know he's a dressy kind too.
Yeah, and my thing is right is that if you're having a good time and like what you're doing, then do it, right? So yeah, he likes to wear suits and you'll be nice and combed and shaven and clean and everything, and that is very very cool. If he likes that, fine. Um, uh, yeah, I think it suits him. Haha. So all right, well, cool. So yeah, what I thought I would do today is sort of get everybody a little bit dizzy and talk about m- motion. Motion, and I'm reading Uncle Bill's comment here. Yeah, yeah. You know, I I don't. I'm not really plugged into the ebbs and flows of Twitch. Um, So, you know, I'm not obviously as sensitive to those kinds of things as you are, um, Uncle Bill. But yeah, it's going to be interesting to see how these changes that have been made, how they're going to affect all the channels, right? All of them. Is there any sense of like how many Twitch channels there are, and like what percentage is say science, what percentage is gaming? Uh,
You mean like what percentage of gaming and what percentage is educational and stuff?
yeah, I kind of be interested in knowing what those numbers are. But yeah, I just like to know how many Twitch channels there are, and maybe how does that compare to YouTube and all the other ones, right? It's kind of
I like to
interesting.
see Twitch more than just gaming and stuff.
Yeah, it's you know I I think having maximizing choice is what I always try to look for. So having
I watched something on TV one time and it says Twitch is not a gaming platform anymore. They got more than just gaming now.
yeah, well, I mean, I think it's almost always been more than just a gaming platform. It was sort of built for that. But yeah, I mean, those kinds of things, I mean, they're going to evolve. So
I like to see what changes they're going to have in Twitch and what's going to affect the gamers, what's going to affect the educators, whatever.
yeah. Well, here's hoping that
Just
that's
as long as if like either Jills or me does a radio stream, please don't try to take it out.
yeah. I'm hoping that there is room for everyone, right? On any and all platforms. So yeah. I think okay. So every viewer has a channel. Okay, so same as YouTube. That's cool. That's cool. All right. Well, as I said, I think I wanted to get into motion a little bit today. And I guess the first thing that I wanted to uh, look at was sort of our I guess you can call it sort of our local motion, right? I mean there are I mean everything is moving, right? Um, Relative to each other, you know, everything in the universe appears to be in motion, right? And so, what I like to do from time to time is sort of think about that motion and actually try to quantify it as as well. There we go. Um, and so what I like to do from time to time is sort of take a step back and look and see what our sort of personal motion is as time goes by, right? Um, and so what I like to do is I like to look at sort of the three primary motions that we experience on a daily basis, and that is motion, um, the motion of ourselves, right, sitting on this planet and rotating, right, going around once every single day. So I'm gonna share my screen here, And let's try to be a little accurate with these numbers instead of just sort of guessing. I'm actually going to look up some of these numbers and see if we can make some relatively accurate calculations. So I'm going to share my screen. Oh, share my screen. And we're going to go to here. This is where I'm just going to be writing everything down. So let's see. All right, so let's go to, and we're going to go to Earth. Not Google Earth, just the regular Earth. Because what I want to do is I want to get the circumference of the Earth. And maybe the circumference at the equator. So here it is. So let's decide to keep our units metric. And that's sort of an arbitrary choice, but let's go ahead and
Uncle Bill, I guess I should specify every login viewer, which means no account equals no channel equals no post.
Okay, cool. So, all right, so the equatorial circumference of the Earth is 40,075.017 kilometers. So I'm just going to punch that in right here, like that. We'll keep the units. So if the Earth rotates once every 24 hours, right? And it's, I guess yeah, I mean, this is where things start to get a little funny, right? Because I think I definitely want to do once every 24 hours because that's our measuring stick. This isn't this isn't a case where we're doing like a sidereal day or a solar day. We're just talking about a regular 24-hour period. So that's our measuring stick. So at the equator, then our velocity would be our circumference divided by 24 hours, right? So 40,000, and I've grabbed my handy dandy calculator here. Now, all good scientists, right, have a actual hand calculator within arm's reach at all times. So 40,075.017 kilometers divided by 24 hours is 1,669.79 kilometers per hour. So that's trucking along pretty good, right? Now, that velocity changes as a function of latitude, right? So at the poles, at the North and South Pole, you're technically not rotating at all, right? And at the equator is sort of the maximum. So if you're either north or south of the equator, you're going to be going a little bit slower than 1,669 kilometers per hour. So let's just use our imagination a little bit and put ourselves at or very, very near the equator. So that's moving pretty fast, right? I mean, that in and of itself, right? I mean, over the course of a day, right? What that means is that all of us, travel 40,000 kilometers in one day. So that is quite a distance, and I don't know about you, but I don't feel a thing. So I don't know, it's got to be really, really smooth or something, right? So that's one kind of motion, right? That's us standing on the Earth, just rotating on the Earth's axis. The next kind of motion is the Earth, which of course we're standing on, revolving around the sun, going around the sun once a year, right? So let's see, how can we do this? I guess because the path of the Earth is an ellipse, right? It isn't a perfect circle. It's really, really, really close to a perfect circle, right? But not exactly. But let's just again, use our imagination a little bit and say, okay, let's make it a perfect circle, because that way it's a little bit easier to compute the circumference, right, which is the distance all the way around, which is what we want. So in doing that, let's go back to the Earth and let's see. Let's just use the semi-major axis, right? Which is the longer of the two axes in this ellipse. Let's just use that number for our radius, our distance from the sun. I'm going to copy that, and I'm going to put that over here like that. So that's 149,598,023 kilometers. So that is the distance between the Earth and the sun. Now, what we want, of course, is the circumference of the circle at that radius. So the circumference is just twice the radius times pi. So it's the diameter of the circle, so 149,598,023 times 2, and then multiply that by pi. And we get, so the circumference here is 939,952,100.1 kilometers. So what is that? That's 939 million, almost 940 million kilometers is the distance that the Earth travels in 1 year as it goes around the sun. Okay, so now let's convert that to kilometers per hour, right? So we already have one for the rotating Earth. Oh, let's see what we're going to use for that. There we go. Okay, so now let's compute our velocity as we're moving around the sun, right? So let's convert that to kilometers per day first. So 939, whoop, there we go. So let's just assume 365.25 days in a year, right? So that's 257,344,8.6. So that's 2.5 million kilometers per day. And that's going to be, so then I can divide that by 24, because there's 24 hours per day. So we're talking 107,227.02 kilometers per hour.
And before you continue, check the chat.
I'm going to check the chat. Check the chat. What's going on in the chat? Yeah, yeah. I totally agree with that. Yeah, I think well, viewing things on YouTube, I don't think you have to have an account either. I don't know how that works though. So, all right, I'm gonna keep going here. So,
what's crazy is if you have a Google account, you also do have a YouTube account.
Yeah, that's very, very true. Okay, so now we've got our how fast we're spinning around on the planet. We also now know how fast we're moving as the Earth orbits the Sun. So let's do one more, and that is the motion of the Sun going around the galaxy. Now, I think for this, what I want to do is go back to Google and see if here we go. Well, that's exactly what I was looking for, in fact. In fact, they actually computed here already, but I'm going to recompute it just for fun. So the mean distance from the center of the Milky Way, they say, is 2.7 times 10 to the 17th kilometers. So that's a little ways out there. 27,000 light years away. Let's see, let's do that. And then we'll do that. Oop. So 2.7, whoop, we had it here, didn't we? Times 10 to the 17th. Let's see, I'm just going to go E17 like that. That means the same thing. And they also gave us, so they say 225 to 250 million years. So let's go 2.25 plus 2.5 divided by 2. Let's go 2.375. So 237 million years. 237, 500,000 years. Okay, so let's work out how fast that is. So let's go 2.7 times 10 to the 17th divided by 237500. So we're talking 1136. Oh, sorry. We have to do one more step here. This is the distance to the center. What we need is the circumference, right? So we need to convert that to a circumference. So we do exactly the same thing, right? We do 2.7 times 10 to the 17th times 2 to get a diameter. and then we multiply by pi. It's not going to be much different, right? 1 point, let's go 696 E18. Okay, so 1.7 times 10 to the 18th kilometers all the way around. Okay, so now let's take that number and divide it into 237. Divided by 237,500,000. And you get some insanely huge number, 714,298,9612 kilometers per year, which is, let's get into days, so that's 365.25. So that's 1,955,6,439.73 kilometers per day, and divide that by 24 to get 814,851.66 kilometers per hour. Wow. So if we add all this up, right, we're going to get 814, 851.66. That is the motion of the sun going around the galaxy. 814,000 kilometers per hour. Then we're going to add to that how fast the Earth is revolving around the sun, which is 107.227 kilometers per hour. 227.02. Okay, and then we're going to add our 1,669.79 kilometers per hour. That's a minuscule amount, 669.79. And we get grand total is 923,748.47. So almost a million kilometers per hour. Right? Kilometers per hour. Almost a million kilometers an hour. That's pretty amazing. So over the course of 24 hours, right, we'll have traveled, so for 24 hours, 24-hour travel time is 22,169,963.28 kilometers. Wow. So in one day, just sitting here, right? Sitting here doing almost nothing at all, I and you and everyone else on this planet have traveled at a minimum, right? At a minimum, 22 million kilometers. So I think that's pretty extraordinary. It's pretty amazing, you know, to think about that. I mean, we're really trucking along, right? I mean, we're moving. You know, let's sort of put this into maybe a little bit more of a perspective here, right? So 923,748.47 kilometers per hour, right, is 256.6 kilometers per second. So that's trucking along pretty good. I hope I've got all my numbers right there. There's that one. Yeah, and there's this one, right? So that's our 3 right there. So then I can do that. I think that's right, because that's this. So 923,000 is this plus this plus this. And then I just divided by 3,600, because that's how many seconds are in an hour. And so, yeah, 256.6 kilometers per second. So, yeah, you know, I'm about that far away from Phoenix. So in 1 second, I will have traveled that distance. And you too. In fact, everybody on this planet, more or less, right? There's a little bit of a correction here, right, in terms of where you are on the planet, right? And there's a little bit of a correction here, depending on, you know, what part of the orbit you're in, because it's an ellipse, right? Sometimes we're moving a little faster, sometimes we're moving a little bit slower. This is just assuming, you know, constant velocity. And this number is, you know, obviously by far the largest number. It's probably also the most uncertain one. But put together, right, I'm coming up with every single day we move about 22 million kilometers. So that's pretty extraordinary. I think that's pretty amazing, and you know, it's for me, that oftentimes sort of puts things into perspective a little bit, because I mean, it certainly doesn't seem as though we're moving like that, and yeah, I mean, relative to the Earth, right? We're not moving at all, or very little. But relative to just the center of the galaxy, right? That's what this motion is. Relative to the center of the galaxy, we're moving along. We're moving along pretty darn fast. Pretty darn fast. So yeah, I think I've done that calculation on this live stream once before, and I think we came to pretty much the same numbers. I don't think I looked up any of the actual numbers. I just sort of guessed, and I think we came up with, you know, more or less the same. 20 million, 22 million kilometers per day. So yeah, pretty amazing. Pretty amazing. So yeah, speaking of motion, one of the other things, as I said, this is sort of a motion live stream. Going to get you dizzy. Going to get you thinking about moving a little bit. One of the projects that I worked on several years ago was looking at the motions of the 4 Galilean moons of Jupiter, and just you know, looking at them in many different ways. And over the course of weeks and months and stuff, I actually came up with a number of scripts that I could just sort of run, given some input, and these scripts would, you know, create plots and graphs and tables and all kinds of information about the motions of Jupiter's 4 Galilean moons. And so, and I think I've shown you all this here before also, but I think it's been a while, so I thought that I would just go ahead and do that again. So what I do is I start with the JPL Horizons website. And as you recall, this is a great place to get the ephemeris, or the positions of various objects, solar system objects, spacecraft, moons, asteroids, comets, all solar system bodies. And so what I do here is I collect the XYZ positions of Jupiter relative to the Sun and relative to the Earth, and then also the positions of the 4 Galilean moons relative to the Earth. And so when I do that, I come up with, let's see, which is the best one to show, this one. I come up with, these tables, which you've seen many, many times. Let's just do Jupiter, Earth. To Jupiter. Oh, come on, machine. Jupiter, Earth. There we go. So, as you can see, it's just the date and time, and then the X, Y, and Z position in kilometers. And this is what Jupiter to Earth. All right, so Earth being at 0, 0, 0. This is the distance of Jupiter from Earth in X, Y, and Z for one day, right? So actually for today, the 27th of September.
This is only for today, right?
Just for today, yeah. That is more than enough information. But as you can see, each data point is each minute. So I've got 1,440 data points here that go through the entire day. Right? There's 10 o'clock, 11 o'clock, 12, 13, 14. Goes through the whole day, right? So, and I've got that for Jupiter and each of its 4 Galilean moons. Then I've got a bunch of scripts. I've got a bunch of scripts. They're Perl scripts, GNU plot scripts, just a kind of a messy sort of arrangement there. But I basically just have to run one script, and it runs all these other things. So it's pretty automatic. And what comes out of it is a whole bunch of stuff. But I was just going to show you the plots. And I think what I'll do is I'm going to just sort of page through these and see which ones I want to start with. I think I want to start with this one. This one here. So,
welcome, Rael.
Hey there, Rael. Nice to see you again in the chat. I'm gonna look at the chat really, really quick. Okay. Yeah. We are always going somewhere. Definitely. So, and actually, what I'm going to show you first is this. Okay, so this is the view of Jupiter and its 4 Galilean moons as it appeared at 0 hours UTC today. So, 2 hours and 44 minutes ago, we had Jupiter here, Europa over on the east, Ganymede just barely on sort of the edge of Jupiter there, Io out to the west, and Callisto even further out, right? So now I'm going to switch views. So this is the view from the Earth, right? This is our view. This is a plot of the positions of those 4 moons as seen from above. And in this particular case, the Earth and the Sun are this away. So I forget which line is which. One of these lines is pointing to the Earth, one is pointing to the Sun. I forget which is which. But as you can see, and this is going to take a little bit of mental dexterity here. So here is Jupiter in the center, right? We've got, oh, you know what? Hold on. My mistake. The Earth and the Sun are this away, right? So at 0 hours UTC, okay, let me explain this a little bit more too. So you can see these curved lines, right? Well, these are the paths of the 4 moons over the course of 24 hours, right? And each of these black dots represents 6 hours. So here's 0 hours UTC, here's 6 hours UTC, here's 12 hours, 18 hours, and of course 0 hours tomorrow. So this is the motion of each of those moons of Io, right, and Europa, and Ganymede, and Callisto over the course of 24 hours. Okay, so as you can see, okay, if we're looking at this system from the Earth, which is this away, right? I'm pretty sure that this green line, which might be a little bit hard to see that it's green, but I think this one here is the Earth line. And I think this line here is pointed towards the Sun, as I recall. But so if you look at the system at 0 hours UTC on from Earth's point of view, well, what you see, right, is that at 0 hours UTC, Jupiter's here, Ganymede is just to the east of Jupiter, Europa is also, sort of just to the east, Io is on the west, and Callisto's on the west. And that's exactly what we're seeing here, right? But now we know that Ganymede is actually on our side of Jupiter, right? It's between Jupiter and us. And Europa is on the other side of Jupiter, right? So, I mean, one wouldn't know that looking at this, right? But Europa's on the opposite side of Jupiter, and Ganymede is on our side of Jupiter. And so, as you can see, over the course of 24 hours, Ganymede is going to be moving west, and Callisto is going to be moving west, and Io is going to reach, its maximum distance from Jupiter, slowly moving west, and then it's going to start moving east again. And for the most part, it looks like Europa is moving mostly east, right? I mean, it also goes through this furthest distance from Jupiter, and then it starts to come back in at the end of the day. So that's just a a different kind of a perspective, right? On looking at the motions of these four Galilean moons of Jupiter. And as you can see, Io moves through a substantial portion of its orbit, while Callisto just does a little bit, right? And I think, trying to remember exactly, I think one orbit of Io is something like 40 hours, and I think one orbit of Callisto is something like 14 days. So that's a little bit of perspective here. So now let's dive in a little bit more and see what we can get here. Let's see. Is that a decent one? I'm trying to get a relatively decent perspective here on things. Io to Jupiter. Yeah. So we can do that. So what this plot is showing, this uppermost left plot, is the distance between Io and Jupiter over the course of the next 24 hours. And as you can see, it starts off at a certain point and then gets, as far away as it's going to get, and then it starts to come back. Because as I said, these orbits aren't perfect circles, right? They're ellipses. Oh, I've got a couple of these up. So every single time these moons go around Jupiter, they're going to go through a furthest distance, which is called the apogee, and they're also going to be close to Jupiter. That's called the perigee. So in this particular case, Io is going through the apogee, what, at about maybe like 11 hours UTC or so. So we can actually look on this map again. I'm going to pull up, I think, how do I want to do this? Let's see if I can find that particular plot. As you can see, these scripts, they pump out a lot of info. Here we go. So I think it said, or it showed, like around 11 hours UTC. Io goes through an apogee, so that's about here, right? That's about here is when it's furthest away from Jupiter. Pretty symmetrical too, right? So I mean, it's when it starts the day, it's at a certain distance, and when it ends the day, it's pretty much at the same, right? So that just means that the distance between here and here and here are more or less the same. It's the distance increases, right, to that point, and then gets less and less and less. What these other plots show are basically just the derivatives, right? So the first derivative of distance, right, is how the distance is changing over time, and that is just velocity, right? Distance divided by time is velocity. So that's what this plot is showing, is the radial velocity, right? So how fast Io is moving either towards or away from Jupiter. And as you can see, when Io is furthest away, its radial velocity is actually at 0, right? I mean, it's like throwing a ball up in the air. At the highest point, the velocity is actually 0, right? And then it starts to fall again. It's the same kind of thing here, right? Same kind of thing here. So yeah, the when the change in distance stops, then of course the velocity is 0. So here, Io is moving away from Jupiter, and then here it's getting towards it again, right? So very, very cool. So all I've done next is just sort of the next derivative up. So changes in velocity is what's called the acceleration. So how much is Io accelerating either towards or away from Jupiter, and that's what this plot is showing, right? So yeah, I mean, it starts to get really, really complicated, right? So as you can see here, we were at a pretty constant velocity, so there's no acceleration, there's no change in velocity at that point. But as the velocity changes, so does the acceleration. And then I can take the derivative of the acceleration and get this term called jerk. So a change in acceleration, I would call that a bump, right? I mean, you can call it a jerk if you want, but I'm going to call it a bump. So that's the first, second, third derivative of distance, right? And then I took the derivative of this, and I get this, and that's called jounce. That's called jounce. And then I can take the derivative of this and get this plot, which is called crackle. So the units here are kind of interesting, right? These units here, distance, is just kilometers, right? These units here of velocity are kilometers per hour. The units of acceleration are kilometers per hour per hour. The units of jerk, as you can probably guess, are kilometers per hour per hour per hour. And then it just goes on and on, right? The jounce is kilometers per hour per hour per hour per hour. And the units of crackle is kilometers per hour per hour per hour per hour per hour. And as you can see, these numbers get smaller and smaller, right? I mean, these are really, really big, right? 420,000 kilometers. Goes all the way down to what, 4 or 5 kilometers per hour in terms of velocity, and then just gets smaller and smaller from there. It's very dizzying, but that is the reality of the situation for sure. This is just sort of an expanded view of that same 4-orbit plot, but it's also showing the position of the Juno spacecraft. So it's way out there, right? Here's the orbit of Io, Europa, Ganymede, Callisto. Here's where Juno is right now, way out there. Think about as far far out as it's going to get this time around. Let's see. So what else do we have here? So yeah, these are just the distances between the 4 moons and Jupiter. And as we already saw, Io went through the apogee already. The other 4 moons are all moving away from Jupiter at this point. See, all these are getting larger and larger and larger, pretty linear too. That's not very exciting. There's that again. There's that again. This is a little bit of artsy stuff that I'm not going to explain. That I'm going to explain at some point. So the other thing I can do, let's so these are the relative motions, or actually the relative distances between the 4 Galilean moons, right? So as the moons orbit the planet, I can measure the distance between Io and Europa, and Io and Ganymede, and Io Callisto, and then all the combinations there. There turns out to be 6 combinations, right? There's those 3: Io, Europa, Io, Ganymede, Io, Callisto, and then there's Europa and Ganymede, Europa and Callisto, and then Ganymede and Callisto. So I can measure the distances of all those guys, and so that's what this is a plot of, is just the distances between those. So in this case, the distance between Io and Europa is going from about 1 million kilometers down to about 400,000. So we can actually look at the plot and see that, okay, well, so between here and here is about 1 million kilometers. And yeah, Io is slowly catching up to Europa. So yes, that distance is going to get smaller. And at the end of the day, yeah, it's about as far away from Europa as it is from Jupiter, which is about right.
Okay. I'd just like to welcome Andy Cowley and Ray L. The universe is moving very fast, but to us it seems very slow, except for time that seems to fly by.
Yeah, it's all relative, right? So I mean, it sort of depends on your perspective, and our perspective is that, you know, we aren't really moving, but if you change your perspective a little bit, we are screaming. We are really moving a lot. So that's what the rest of these plots show, right? So here it's actually showing that Io gets as far away from Ganymede as it's going to get, and then it starts to get closer again. So let's see, Io and Ganymede. So here's Io, and here's Ganymede, and yeah, see, look, Io is moving away from Ganymede, and then it starts to move towards it at the end. And yeah, that's exactly what we're seeing there, for sure. Io to Callisto, again, it seems to get as far away from Callisto as it's going to get, and then it just starts to get a little bit closer there towards the end of the day. And yeah, that's exactly what we're seeing again there, right? It's about as far away as it's going to get, and then it starts to get a little bit closer there at the end of the day. Very cool. So Europa to Ganymede, they're just mutually getting closer to one another. Europa to Ganymede. Yeah, see, Europa is going to actually overtake Ganymede at some point. Maybe the next couple of days or so. But yeah, so it's slowly getting closer to Ganymede. Europa to Callisto, it too goes through a furthest distance. Yep, very, very true. Yep, for sure. And let's see, the last one. Ganymede and Callisto are actually getting closer to one another too. And that's because Ganymede is slowly catching up to Callisto. So yeah, it's just, you know, I know I'm kind of flying through this fast, but I hope it's giving you a little bit of a perspective on some motion. So, of course, the other thing I can do is I can look at all the derivatives as well. So, you know, here is the distance again between Europa and Callisto, and then I can compute velocities and accelerations and jerks and jounces and crackles as well. So you can sort of see that, you know, velocity is slowing down here, but the acceleration is changing. Yeah, it's complicated. Motion is complicated. So there's Europa to Ganymede, Europa to Jupiter. There's, yeah, some pretty interesting patterns come up. There's Ganymede to Jupiter. Notice how the velocity sort of maxes out here, right? So at that point, the change in velocity is zero, and that, of course, is the acceleration, which is right there, which is zero. Here's Io to Callisto. Again, you know, some really interesting kinds of motion here, right? Io to Europa, Io to Ganymede, Io to Jupiter. I think that's it. We've looked at everything here. So yeah, hopefully that didn't dizzy you too much. It's a lot to take in. I understand that, but that is the fun and joy of doing astronomy. Is yeah, you know, thinking about things in different ways, trying to, you know, get perspectives on stuff where you sometimes you wouldn't. So and thinking about how things move, and how things change, right? And you know what those plots show, showed me at least, is that you know, they always say, you know, that one of the only constants in the universe is change. No, change isn't constant. Change changes as well. Are there actually any kinds of constants at all? I doubt it. I doubt it. Maybe there are, but in terms of motion, not at all. All right, you guys. Well, I think I'm going to get out of here for now. We've been thinking astronomical thoughts for a little while, and yeah, really, really awesome stuff. So glad everybody could come in again. It's always really, really great to have.
And to take it, and I don't want to. The older you get, the faster time will fly. Your neurons fire more slowly with advancing age, when changing your perception of the speed of time.
Yeah, you know, I don't know. You know, I mean, we're talking about perceptions of things, which are basically measuring sticks.
And Ray Ann wants to know about your scope.
Oh, the scope behind me there, Ray. That's a Celestron Nextar 8. Yeah, that's my new babe. So had that one for I guess I've had it a couple years now, or so. So yeah, just your basic C8. Yeah. All right, you guys. Well, as I said, I think I'm going to get out of here for now. So thanks for coming in. And yeah, let's do this again in about 22 million kilometers. Somewhere, I don't know, maybe out that way. Not quite sure. So, all right. Take care, everybody. Yeah, well, it would look a little more cool if I didn't have a bag on top of it. So yeah, sometimes flat surfaces here, are much wanted. So if there's any kind of flat surface at all, I tend to put things on it. So don't necessarily like to use the scope as a table, but yeah, it was it was there. So all right. So take care, everybody. I will see you on the spin in a little less than 23 hours. All right. Take care. Bye.